All right, so next we're going to take a look at another method of solving these problems, right? You know, last part in this lecture, we sort of looked at sort of analogs of the power rule for integration and the sum and difference rule and exponentials. Um, and for the rest of this lecture, we're going to look at the analog of the chain rule. Okay, and it's something called integration by substitution. Um, the other thing that you'll hear it called is U sub. U substitution. It's often just shortened to U sub. Um, and when you use it in combination with the stuff we talked about last time, it allows you to integrate this huge class of functions. Okay, um, and well, let's just sort of take a look at how you would do it, right? Say you're taking the antiderivative of 2 times 2x plus 4 to the fifth, okay? And just as before, you know, when we first talked about the chain rule, you could absolutely um, expand this whole thing out and use the sum and difference and the power rule to work it all the way through, okay? But instead, what we're going to do is we're going to look for some sort of clever substitution to simplify it, okay? And here's the idea, right? Let's let u equal 2x plus 4, okay? Then we want to take the differential, right? Remember way back, I believe it was before the first exam actually, we talked about differentials, and now they're going to actually come in very handy, right? Because du is 2 times dx, right? And here's what I want you to notice, right? Let's rewrite this integral. The integral of 2x plus 4 to the fifth times 2 dx. So what we want to notice here is 2 dx is du, and 2x plus 4 is u. So if we, I guess, rewrite this in our new color, this is the antiderivative of u to the fifth du. And we can evaluate that super easily, right? That's 1 over 5 plus 1, or 6, u to the sixth plus c. And now if I replace my value of u in here, this is going to be 1 over 6 times 2x plus 4 to the sixth plus c. And if you take the derivative of this function, you can indeed see that this is what you get, right? And so here's the basic idea behind why this works. Again, this is the analog of the chain rule, right? So let's say f of x is x to the fifth, and g of x is 2x plus 4, right? Notice g prime of x is equal to 2. Thus, right, notice this guy is 2 times our composition, right? So 2 times f of g of x is 2 times f of g of x, which is once again our integrand from before. right? 2x plus 4 to the fifth. But here's the thing to notice, right? This 2, that's g prime of x, right? So that means that f of g of x times g prime of x, that's the integrand of our equation, right? So the integral from before can be written like this, dx, okay? And what we're looking to do is show that this can be written, right, as f, the integral of f of u du, right? Because that's what we did here, okay? So suppose we have some antiderivative of f, right? Then d dx of f of g of x, right? Since f, capital F, is an antiderivative, well, using our chain rule, we get this, right? The derivative of the outside with the inside plugged in times the derivative of the inside. So that is going to directly tell us that the integral of f prime of g of x, g prime of x, well, is going to be capital F of g plus c, right? And this equality here, right, this just comes from doing our integral on sort of both sides of this equation, right? This integral and this derivative are going to cancel, and then we're going to get a plus c out the other side. But there's two things to notice here, right? Once we have this equation, right, we said that capital F was an antiderivative of lowercase f. So why not just write f prime as lowercase f? Additionally, let's let u equal g of x, right? So we can say that f of g of x, g prime of x dx, right, the thing that we're trying to show, well, we know that that's capital F of g of x, but let's call it just g of x u plus c. Well, by the rule of how antiderivatives work, right, this is going to be the antiderivative of f prime of u du, which of course, if we want to choose a particular f prime, we can choose lowercase f, right? And I know this was technical and a little bit abstract, but this is sort of the idea and the theory behind what we're doing. But you know, we can work through a number of examples here to get used to working with these, because I know that it can be a little bit abstract. Okay, so let's just start a series of examples. Let's say start with 2x times x squared plus 3 to the fourth dx. Okay, and you can sort of loosely break this down into 5 steps, right? The first one is to pick some value of u. And you know, much like when you're first starting to do chain rule stuff, it's a little bit, you know, weird to try and pick what u is, but then as you work with it more and more, you know, you're able to pick out, you know, what should be u a little bit easier, right? And notice here that we have a natural sort of inside part for our function here. So let's try and let u equal x squared plus 3. Right? The sort of second quote step, right, is to find du. Well, my 3 is going to drop, so we're going to get 2x dx, right? And now we can sort of do our third step, right? Let's rewrite this guy as the integral of x squared plus 3 to the fourth times 2x dx. Right. The other way to do this, of course, is to solve for dx and then substitute it directly, or you can sort of do this grouping, right? And once we've done this grouping, we can convert this into an integral in u, right? This is going to be u to the fourth du, because this is my u to the fourth, and this is exactly what du equals. And now sort of step 4, I can evaluate this, right? This is going to be 1 over 4 plus 1 for 5, u to the fifth plus c. And then my final step is this sort of back substitution, 1 over 5 x squared plus 3 to the fifth plus c, right? And that gives us our solution, right? But let's look at something that has a little bit more meat to it, right? What about the antiderivative of 3 times the square root of 3x plus 1 dx? Well, since we're composing a 3x plus 1 into a square root, right, it would only seem natural for us to let u is 3x plus 1, right? Well, then du is going to be 3 dx. So when I rewrite this guy, we're going to get the square root of 3x plus 1 times 3 dx. And this is going to naturally convert into the square root of u, or u to the 1/2 du. And so that means when we go to evaluate this, right, we're going to get 1 over 1/2 plus 1. Well, 1/2 plus 1 is 3/2, but it's 1 over 3/2. So we're going to get 2/3 x to the 3/2, right? 1/2 plus 1 plus c, and that should be u, not x. And now we back substitute, right? We're going to get 2/3. My u is 3x plus 1 to the 3/2, and then my c is, well, my c is a c, okay? What about something like x squared times x cubed plus 1 to the 3/2 dx? Well, this one's going to give us a bit more of a complicated system, and that's because the obvious thing to make is our dx, or our u, sorry, is this guy right here, this x cubed plus 1. So if we let u equal x cubed plus 1, right, what does that mean? Well, that means that du, taking our derivative, is going to be 3x squared dx, okay? And the natural thing that we want to do here is sort of group our things by stuff that looks like u and stuff that looks like du, x squared dx. But notice there's an extra factor of 3 here, right? And so what we might want to do, there's a number of different ways to sort of handle this, but they all, are exactly the same. The way that I prefer to think of it is going here and saying, well, this means that x squared dx is 1/3 du. And now I can perform my substitution directly, right? We can have our integral of u to the 3/2 times 1/3 du, right? Remembering that there's this extra factor of 3 that we need to do something with, right? But of course, that 1/3 is just going to factor through to the front, u to the 3/2 du. And now we can evaluate it, right? Our 1/3 stays. We're going to get 1/3² plus 1, right, which is 5/2. So times 2/5, because it's 1 over that. U to the 2/5, or sorry, u to the 5/2. And then that's plus c. But of course, that's going to simplify, right, to be 2 over 15 times u to the 5/2 plus c. And now I can back substitute, right? 2 over 15 times my value of u, this x cubed plus 1, plus c, where we're going to the 5/2. We can also do this with things like, say, e to the minus 3x dx, right? What's this guy going to look like? Well, once again, we're trying to think about how to build this as a composition of functions. And we can build this as a composition of functions by letting u equal minus 3x, right? That means that du equals minus 3 dx, or that dx is minus 1/3 du. And this is sort of, how I usually do it. As I said with right here, there's a bunch of different ways to make this substitution work. And you should think about it the way that, works best in your head. You could also, sort of going back to this example, you could write this as dx is du over 3x squared, right? And then when you substitute in your dx, this x squared cancels with that x squared, and you're left with 1/3, right? That's generally how I tend to think about it. But as I said, both are just two different roads to get to the same spot. With this value of dx and our value of u, we can rewrite our integral, right? It's going to be e to the u, and that's times 1/3 du, minus 1/3 du. But of course, that 1 over minus 3 is going to factor to the front, eu du, right? The antiderivative of this guy is possibly the easiest antiderivative, right? Because it's just e to the u plus c, right? But now we back substitute in our value of u, and we get minus 1/3 e to the minus 3x plus c. Got two more for you. You're going to have a little bit more, meat to them. They'll be a little bit more complicated. So let's go 3x squared plus 1 is the denominator, and x is in the numerator. And now this is a little bit more interesting, right? We want to pick a value of u, and why don't we pick u as 3x squared plus 1? Let's see if that can take us anywhere, right? Sometimes you pick a value of u. Maybe this happened to you back when we were doing the chain rule, where you picked a value of u and found that it didn't work. Maybe that happened, maybe not. here in antiderivative world, you're going to pick the wrong value of u. It happens to everyone, you pick a value of u, you work it through, and you're like, dang, that super doesn't work, that didn't simplify it at all. And then, maybe you sit there annoyed for a second. Maybe you go and you take a walk because this is the third time that you've tried to pick a value of u, but then, you pick another one and you see if it works. In this case, du from 3x squared plus 1, well, du is going to be, it looks like 6x dx. Okay, my plus 1 is going to just go away. And trying to rewrite this, well, we're going to get the integral of 1 over 3x squared plus 1 times x dx, right? The numerator can kind of go wherever. It can't get down to the denominator, right? But you can, sort of write this dx up there. You can, write it like this. Both work, as long as that we know this whole thing is our integrand, right? So this is telling me that we have an extra factor of 6 here. So we have x dx is 1 over 6 du. Now we can make our substitution. Looks like we're going to get 1 over u du, 1 over 6 over u du, actually, right? Because we have this 1 over 6. But of course, that 1 over 6 is going to factor through, times the antiderivative of 1 over u du. Okay. But we have a rule for this, right? This is 1 over 6 times the natural log of the absolute value of u plus c. But 3x squared plus 1 is always greater than 0, right? We're squaring it so it's positive, and then we're adding 1 so it's never negative. So what that means is when I substitute this back in, I can actually drop my absolute value bars. And that's precisely because the absolute value of 3x squared plus 1 is equal to 3x squared plus 1, right? Let's do one more of these. All right, let's say the antiderivative of the natural log of x squared over 2x. This one seems even stranger. Right? Your first instinct might to maybe let u equal 2x. It might be to let the numerator equal u, but we're going to say u is just the natural log of x, right? Which then means, right, that du is going to be 1 over x dx, right? Because the derivative of the natural log of x is 1 over x. And so du is 1 over x dx. And let's start to look for how we can make our substitutions, right? We can bring this 2 out front, right? Because this is just a 1/2 times the integral of, well, my natural log of x squared stays there. And this is going to be times 1 over x dx. But this is precisely my du. And u is the natural log of x. So this is equal to 1/2 times the antiderivative of u squared du. But we know how to calculate the antiderivative of u squared du. Right? That's 1/2 times 1/3 x cubed. 2 plus 1 is 3, and 2 plus 1 is 3. Right? 3 and 3. And of course, I can, combine those and get 1 over 6 x cubed plus c. Can't forget our plus c. And now we can back substitute, right? 1 over 6, these should all be u's. I don't know why I wrote those as x's. u is the natural log of x. So this is the natural log of x cubed plus c, right? This is our antiderivative. Go ahead, check it. Do your chain rule here to actually calculate the derivative of this guy. And this again, u substitution is, it's tricky because you have to be able to see this, right? And that's the thing that just comes with time and practice, right? And calculating a bunch of these integrals. Eventually you're able to see this. This one right here, u is not obvious here, right? There's a bunch of things that you might be tempted to set u as. Like I said, 2x at first glance seems like a good candidate. That's what we did here, right? We just let our denominator. Again, setting u equal to the natural log of x seems like an obvious choice. But if you go down either of those roads, what happens is not all of the x's cancel, right? And that's the really important thing that we're doing with this u sub, right? If when you work this through, going all the way back to this theory page, if you can't write it just in terms of u, your substitution doesn't work, right? If you get something that's like, f of u is 3u squared plus x, that doesn't work, right? Your function has to be totally in terms of u. And so this differential here, this has to cancel with whatever you have elsewhere in your integrand. Okay. That's going to finish our lecture for today. Come back on Thursday. We'll sort of look at another view of what integration is doing, and then hopefully, dependent on time, we'll get to see something called the fundamental theorem of calculus, which, from its name, you would guess is, well, pretty fundamental to the study of calculus. So I'll see you then.